Log on, tune in, find out. Another good idea from Cambridge.
The next talk, just a quick announcement. After this talk, we will have a conference picture taken just outside here. So after the talk, just please don't run away for your lunch. We would like to take this picture.
Okay, the next speaker is Daniel Juteau from CNRS, and he's going to talk about Perverse, sheaves, and modular representation theory.
So it's a great pleasure to talk in this conference and to have spent some time here. It's one of the places where some of me and my co-authors met, and it's also a place where I could ask questions to experts when it was needed. It was always very useful. So it's about Perverse sheaves and modular representation theory. And it is joint work with Karl Mausner. And Jordi Williamson. So if you look on arXiv, you can see two papers. One with this title, and it provides like a survey of this kind of thing. And there are some definitions where we insist on what is different in positive characteristic, and some very concrete examples and references to, of course. And this was for the proceedings of a summer school in Grenoble. So if you want to see very concrete examples that you can work out for yourself or follow, it's a place to look at if you want. And otherwise, there is another article which was posted recently, which is called Parity Sheaves. And I will also talk about this in this lecture. So first, I will talk about representation theory and perverse sheaves. In characteristic 0 versus characteristic P. So if you look at categories of representations, like of reductive groups or related objects, this often gives rise to some singular varieties. And you will look at categories of perverse sheaves, which capture the geometry of these singularities. So you will have some variety with some stratification, usually. And the closures of the strata will have singularities. So this has a long history. So the first occurrence, the causal-acoustic theory, where you look at category O for Lie algebra, and with a Bellinson-Bernstein localization, you go to perverse sheaves on the flag variety, finite flag variety, with the Schubert cells. Another example is a Springer correspondence. Where you look at representations of W, the Weil group. And with this Springer correspondence, you go to the nilpotent cone inside the corresponding Lie algebra with a, and this is the G equivariant setting. And you have stratification by a finite number of nilpotent orbits. So, and this was generalized by Lustig. And this further led to character sheaves. Which has perverse sheaves on the group G to calculate character values for finite reductive groups. So, and there are many other examples. There is a nice talk by Lustig in 1990, which is called IC Methods in Representation Theory. Where there is an impressive list of such applications. So, this kind of approach is amazingly powerful. So some reasons for this. Of course, is the weights, the purity, and the decomposition theorem, which is in the fundamental article of Bellinson, Bernstein, and Delin. So, for example, the simple objects among perverse sheaves are intersection cohomology complexes, and we have a distinguished class of objects. Which we can call semi-simple complexes. So it's a direct sums of sheaves of intersection cohomology sheaves. Well, this class is stable under proper push forward. And for example, so you can often calculate inductively the intersection cohomology sheaves, or what you are interested in is the Stokes. If you know the Stokes, normally you are happy. And for example, the kind of things for causal-acoustic polynomials. But of course, much of this breaks down in characteristic P. So I will mention some connections between modular representation theory and perverse sheaves with coefficients in characteristic P, but the base field for the geometry, for the varieties, can still be the complex numbers. So if you consider flag varieties, and their affine counterpart, there is a work of Zergel and Fibish on Lustig conjecture. So Peter Fibish talked yesterday about this work. So I'm going to mention, so I will come back to this later, but I'm going to mention other works for other relations. So there's a geometric Satake correspondence. So if you look at representations of a group or over a very general commutative ring, actually, so you look at this as a group scheme, it will be equivalent to a certain category of perverse sheaves on the affine Grassmannian, so, but for the dual reductive group. So if I introduce this field C of t and the ring of t integers, the lower series, then we look at the dual Langlands group over C of t. And the affine Grassmannian is GR Gch of C of t modulo the points of the Laurent series. So we look at this and variety. So it's infinite dimensional, but you can take coefficients in K. And this is an equivalence. So for K equal to C, was a succession of work of Lustig, Bellinson, Drinfeld, and Ginzburg. But in this generality, it's a work of Mirkovic and Vilonen. And this has very nice properties. For example, standards goes to standards, goes standards as well. For another relation, there is a modular version of the Springer correspondence. This was done in my thesis. But if what you are interested in is to solve the problems, what can you get? Because you have equivalences, but what does it give you? So you can get things like if you knew the Stokes of orbit closures, so say GR sub lambda bar, so for intersection cohomology complexes with coefficients in FP bar, say. Then you could take the Euler characteristic, and this would give you the weight multiplicities. for the modular simple modules. Or similarly, so if you knew, okay, if you knew the Stokes of intersection cohomology complexes of nilpotent orbit closures and coefficients in some local systems, in characteristic P compared to characteristic 0. Well, you could find the decomposition matrix for the Weil group in this way. So actually, the decomposition matrix for W is included in some decomposition matrix for equivariant perverse sheaves and the nilpotent cone. But of course, there is an if. So the problem is that intersection cohomology Stokes are very difficult to compute in general in characteristic P. And well, the main reason probably is that the decomposition theorem fails, if you want. So the same statement with characteristic P coefficients doesn't hold. And so our motivation is to understand this failure. And maybe find a replacement. And to get something which is both interesting and computable, or more easily computable. Well, there are some a few calculations that are done. For example, in finite flag varieties, well, you can work at for B2. If you look at the flag varieties, there is an A1 singularity, and then it's possible to see that the decomposition theorem will fail there. But you can compute these Stokes. But in simply, so this is B2, but it's not very astonishing. There is a problem with 0.2 for B2 right, because of the double edge. But for simply lay steps, it's only in recently that Boyden found two torsion in types A7 and D4. He announced it in Oberwolfach in 2004, but there's no preprint available, but it's some computation. Otherwise, there's some more general attempts, like to prove that there is no torsion in many cases. So in Jordi Williamson's thesis, there is an algorithm using W graphs, and as long as it works, there is no torsion. And so it works quite well in small wonks. Otherwise, for nilpotent cones, for example, if you look at G simple, you have two extreme cases: a regular class and subregular class on the one hand, the minimal class and trivial class on the other hand. And these are classes that make sense in all types. So you can hope that there is a beautiful answer in terms of root systems, and that's the case. So when there is likely to be a beautiful answer, it's more worth doing it, but otherwise it's a bit discouraging. So even for SL3, P equal 2, we needed to be the three of us to complete the calculation. Actually, it would be much more efficient to use representation theoretic facts to compute the Stokes, because this would give, in that case, the Stokes. But for SL3, P equal to 3, Carl did the calculation without using representation theory, and he had to use 3 spectral sequences, and so it's very complicated and discouraging for SL3. So we want to understand why it is difficult, so why we have this failure of the decomposition theorem. So there are at least three proofs in characteristic 0. So there's a proof in BBD. So first, you go from the base field from C to the algebraic closure of a finite field. And then you use Frobenius and weights. So it's arithmetic. And then you go back to C. So it's a bit magic. Then there is a Sato approach with mixed Hodge modules. Which is a huge machinery and quite involved. So for the years, it's like 81, 89, 90. But then there is a more recent proof of Di Cataldo and Migliorini. So first, in 2002, for semi-small maps. So these are maps that have fibers whose dimensions are not too big with respect to some stratification. And they have the property that the direct image of a perverse sheaf stays perverse. And then in 2005, they find a reduction to the semi-small case. And they call this approach from a classical Hodge theory. Actually, in the different approaches, they don't prove just the decomposition theorem, they prove other results at the same time, like the relative hard left-side theorem or such thing. So then you can try to see why this fails in characteristic P. So you can still consider weights in characteristic P. Let's say, yeah. Usually P is a prime that divides Q, so you would take another prime L different from P. But so Zergel told me an idea that, so a student of his tried to do this. So the problem with the weights in positive characteristic is that they turn in a circle because the line is finite. But if the circle is big enough, it's almost like a line. And so if you try, you want to try to see how large it has to be so that the argument still works. So I think his name is Komenko, but he wrote something down, but I don't think anybody really read it and believes it. But it's for Schubert varieties, so the geometry is very particular, so maybe there is some hope to do something in this way. But in the De Cataldo and Migliorini approach, there is something very interesting. So the De Cataldo and Migliorini, an ingredient of the proof is the following. So you have some, so you have, say, for a semi-small map, and proper. So semi-small means that you have the stratification, but if you take an x lambda in x lambda, the dimension of the fiber is at most 1/2 of the cone dimension of x lambda in x. And the strata where you have equality are called well events. So this already appears in Borrow-McPherson for Springer correspondence with Perverse sheaves. And if you look at the top Borel-Moore homology of the fiber, it has a basis. So I take a well-event strata. So the basis is indexed by irreducible components of maximal dimension. And this comes with some geometrically defined bilinear form, which is an intersection pairing. So in characteristic 0, Di Cataldo and Miglioni says there's a polarization. And this implies that the forms are definite. And in particular, they are non-degenerate. But the very interesting thing for us is that they point out that the decomposition theorem holds precisely because of this. So let me write it down anyway. And also, you want the local systems to be semi-simple. Is that up here? But in characteristic 0, this is automatic. Because you have a representation of the fundamental group, but it permutes the components, so it has two factors to a finite group, and we are in characteristic 0. But with this formulation, of course, this will make no sense anymore. But this will give us a criterion to see when the decomposition theorem holds. And actually, it's so I said understand the failure, but we even hope to measure the failure, like to compute the Wank. Obviously, you have a matrix of a bilinear form defined over Z. You can reduce modulo P. And then I can say slopily that more or less splitting will occur according to the ranks of this bilinear form. So look at the intersection matrix mod P. If they have full Wank, then you get the same answer as in characteristic 0. Okay, but so we want to. So the decomposition theorem does not hold. We won't have, in general, a direct sum of intersection cohomology sheaves. So we want to find a replacement to decompose into indecomposables. But what are the indecomposables that appear? So the question. What indecomposable appear? Because if you have this semi-small resolution, you can do like an inductive procedure. You start from an open stratum and you add strata. And then you can see that there is some splitting at some point. But then as you go further, you don't know how it will behave. It's not clear a priori what will happen in general. But now I will talk about a work of Zergel in 2000. So the title of the paper is On the Relation between Intersection Cohomology and Representation Theory in Positive Characteristic. So this is for flag varieties. And so you consider a subcategory K full in the constructible derived category. So it's constructible for the usual stratification with the orbits of the Borel, the Boa cells. And so which contains, which is generated, say, by direct images of the constant sheaf on both semestral resolutions. So these are the things that you want to decompose anyway. So and together with shifts, direct sums, okay, so get the category. So here there is really the idea that intersection cohomology sheaves in characteristic P are too complicated. We are going to replace by something else that behaves a little bit like intersection cohomology sheaves in characteristic 0, and which are the indecomposable summands that appear here. So actually, enough to consider. So for each simple reflection, you go from G mod B to G mod minimal parabolic subgroup associated to S, call it pi S, and you use push forwards followed by pullback with different kinds of simple reflections. You start with a constant sheaf on the point. You do this as long as you want with different reflections and take direct summands and shifts. And this gives you the same. And so it classifies the indecomposable objects. So for all y in W, there exists one, so up to a isomorphism in the composable L of y in this category, which extends the constant sheaf. And we put it in the correct degree. So in that way, with the uniqueness, you can see that they are self-dual under Grothendieck-Verdier duality. And so this is a classification theorem. And now they are interesting for representation theory. Like, so if you look at multiplicities in induced modules of some specific for some specific weights, so it's a one the Steinberg weight. So if you look at Steinberg plus x times rho for some element of the value group, if you look at the multiplicity of some simple, then if you know the Stokes of this indecomposable sheaves, then you can answer this question. So you get the sum over I of the dimension of a car. So if you have the Stokes, hi of L of y, look at the Stoke at x. So in that paper, you find the following lemma. If you take f, a complex, so it is in the derived category, and which is constant along B orbits, and which has cohomology sheaves only in even degree. And if S is a simple reflection, then if you do this simple operation, then you will still have this property. And Zogel says this comes from a Bourbaki seminar from Springer, who says it comes from Macpherson. And so, for example, as a corollary, any f in K can be written as a direct sum with even part and odd part. So here we can see some ideas that will be developed. So we want to understand the direct summons of direct images under resolutions. But we don't consider random varieties. We are representation theorists. And so the resolutions are very specific properties that don't occur for random varieties. For example, these Botsamesson resolutions, they have a parity property, which makes such things possible. So, since this doesn't only happen for flag varieties or the generalizations, but also for the Springer resolution, for example. There's a paper of De Concini, Lustig, and Procesi, which says that the cohomology of the fibers is free and in even degree, so it's even for all coefficients, and for toric varieties as well. And so we'll introduce parity sheaves, which have some nice properties. So we have some conditions on X with a stratification, but which are often satisfied in representation theoretic situations, and which have the following good properties. So if you look at direct sums of shifts of parity sheaves, this will be stable by some proper push forwards, those that have this even property. So by even proper push forwards. And also, in some cases, you can do an inductive calculation. So actually, Peter Fibisch already talked about this in his talk. So with Jordi, they have a paper in preparation. With so parity sheaves answer the following question: what do moment graphs compute? So this will make the junction between parity sheaves and Fibisch work. And for this moment graph, there's an algorithm, the Boyden-McPherson, so which gives you intersection cohomology sheaves in characteristic 0 for the varieties with the nice properties. But if you apply it with coefficients in characteristic P, this is what you will get under these conditions. So I'll go to the general setting. So X is a complex. So we work in two frameworks, either equivariant or non-equivariant. So we can put brackets, G variety. So either with or without G, with a fixed stratification. And we assume it is Whitney. So in particular, the strata are smooth, and the closure of a stratum is a union of strata. And we take K a field of characteristic P. But actually, we also work over, for example, extension of ZP. So our conditions are satisfied, for example, for flag varieties satisfied by Schubert cells, the nilpotent cone of GLN with the GLN equivariant setting, the affine Grassmannian, and also for toric varieties. So now here is the definition. So if you have a complex P, so we work in the Giraffe category, of, which is S constructible. So it will be even if the cohomology sheaves are non-zero only in even degree, and the same for the dual. And the same definition for odd. And parity will mean either even or odd. And so I will say now the assumptions that we need. So say for K a field, for if the a ring we also want freeness. So we want that the cohomology of the strata may be equivariant if it's in an equivalent setting in any local system is in even degrees. So actually the idea is the following. So for example, you have deep theorems of the line with weights which tell you that some spectral sequences degenerate in a Leray spectral sequence. But also, so this is very deep, but also sometimes spectral sequences, for example, degenerate for very elementary reasons, for parity reasons, for example. So with these conditions, and it's reasonable to consider this because it happens all the time in representation theory, you can get things without the theory of weights, but with parity considerations. And so the very beautiful thing with this definition is that with these conditions, you have a very nice classification, like for intersection cohomology sheaves. So you have this following uniqueness theorem. So given a pair, say x lambda L, where x lambda is a stratum and L is some local system, maybe J covariant. Local system on x lambda. This condition implies that there is at most up to isomorphism one parity complex, indecomposable parity complex, which we'll call E, like even, lambda L, such that when you restrict to x lambda, you get the local system you started with, shifted by the dimension of lambda. So I will call d lambda. This is the first thing. And the second thing is that up to sheaves, this is all. So any indecomposable parity complex is isomorphic to some E lambda L shifted with some shift for some lambda L local system irreducible. And some shift. So why do we normalize them like this? So first, we call them parity sheaves. So like for perverse sheaves, we use the word sheaves, although it's a complex, but it has a property that if you do a non-trivial shift, it will not be called sheaf anymore. And you can see that with this uniqueness theorem, the dual has to be also a parity sheaf for the dual local system. Sorry. Thanks. So almost all the time we have even resolutions, and so now we know which indecomposable summons appear. These are the parity sheaves, and they are uniquely determined with this property. Next, we have the following results. So, as I said, the direct image of a parity sheaf under an even proper map is again parity. And so now observation. So assume that all intersection cohomology complexes are parity. Well, if you take if you take an even resolution, you should take the direct image of the constant. It has to split into parity sheaves, but or at least up to sheaves, but they are all IC sheaves. So in this case, the decomposition theorem holds. Actually, with this assumption, the semi-simplicity of local systems is automatic, so we get away of this problem as well. Okay. And so, in the semi-small case, for each lambda, you associate a local system, a lambda, which is h minus the dimension of the direct image. Okay. And you have a bilinear form on this local system. So if you look at a stalk, at some point x lambda, you get the top cohomology, the top Borel-Moore homology of the fiber with this intersection pairing. So in the semi-small case, so if all the B lambda are non-degenerate, then you will get the decomposition theorem. But in general, you have that this direct image. It will be so. I'm still in the even proper case. It will split into a direct sum of parity sheaves, but the multiplicities are given by these local systems. So you will have some E lambda, L lambda mod the radical. So the multiplicity of the indecomposable corresponding to L lambda is the multiplicity of this local system in this. So this is the form the decomposition theorem takes with parity sheaves. So for the applications, so first we have existence and uniqueness of parity sheaves in the following cases. So we can take flag varieties even in generalized sense. So that kind of things, but in the equivariant setting, we might have to take away some torsion primes, but they are small. Then you can consider toric varieties. And for example, the nilpotent cone in JLN. So you have uniqueness in general types if you stay away from some torsion primes. So there's a known list of torsion primes. But for the existence, so you have this result of De Concini, Lustig, and Procesi for the Springer resolution, so the nilpotent cone. But if you take a general nilpotent orbit closure, there is a standard resolution, but we don't know if it is even or not, in particular over Z. But for example, for nilpotent cones, we know that intersection cohomology sheaves are even, so they have to be so in almost all characteristics. But for a given characteristic, it's always difficult to know what happens.
So there is no exact statement about the fibers, which are even, of course, right? But probably there's something. What else can we know about the fibers?
You want that the cohomology is concentrated in even degrees, and maybe that it is well behaved with respect to the stratification, so it's stratified morphism. So, but
no I see considerations, just pure algebraic geometry, right? Some conditions on the fibers, right?
yes, yes.
Which are satisfied in the cases which you listed.
Yes.
Okay.
But for example, for resolution of a general nilpotent orbit closure, I don't know for which primes they are even. And yeah, even in characteristic 0, I'm not sure. But for Richardson orbits, it might be easier. For example, in type A, it's not. Yeah, for GLN, it's okay. For Ota Shimomura, it's paved by affine spaces. But the most interesting is for the affine Guatsmanian, so it's a particular case of affine generalized flag variety. So here's the following theorem. So if the characteristic is bigger than some bounds, which depends on the type, but certainly if P is greater than H+1, but you can do better, then the parity sheaves, so a priori there are indecomposable objects in the derived category. So you don't even know if they are perverse sheaves, but the first thing they are perverse. And so you can look at the image under the geometric Satake correspondence, and they correspond to tilting modules. And actually, in that case, we could call them tilting sheaves. So in a way, it's in the same sense as Bezukradnikov, Mirkovic, and another author, but instead of J shrieks, you want Romanian? Yeah, Romanian. maybe Bellinson. You want filtrations by PJ shrieks and PJ stars because now the strata are not affine. And so you don't have a priori, you don't have a local criterion to know if they are tilting. For when the strata are affine, you just consider restrictions to strata and they have to be local systems in minus the dimension. So it's a local criterion. But now the fact to be parity is a local criterion. So a remark, so to prove this, we go through representations. So we use the fact that we know what happens geometrically for minuscule weights and for higher short roots. But it's not a direct proof. But it is known that we use this fact that tilting, tensor tilting is tilting. But we can prove that parity convolved with parity is still parity. So actually, it's a generalization of the lemma which was in Zörgel's paper in this affine context. And so if there was a direct argument that these are tilting, correspond to tilting modules, this would give another proof that it's stable under tensor product. And I'll just say a few more remarks. There's a conjecture of Mirkovic and Vilonen. So the IC for the affine Gaswanian with coefficients, say, in ZP are torsion-free. The Stokes. And I added for P good because otherwise there are counterexamples. And actually, this would imply the theorem for any P where it would be true. And one can wonder whether one could prove an inverse implication. And we have a general conjecture is that the pH0 of a parity sheaf corresponds to the tilting modules. So we have some examples where this is not perverse, and we really need to do that. And this works for the higher short root, for example. And so with this example, I hope you can see that parity sheaves appear in several contexts. And moreover, so we have more hope to calculate them. So the thing with the bilinear forms is not very convenient because you have to understand how the components of the fibers intersect. But with a moment graph approach, normally you can write a computer program. So there's some hope for computations. And also for toric varieties, there is an algorithm for intersection to compute intersection cohomology in characteristic 0. And we think that if you do this algorithm with characteristic P, you also get parity sheaves. So it's another instance where you can calculate, hopefully. Thank you.
Thank you.
Questions or remarks?
So can you characterize this the tilting module? How about the bar module?
And the geometric statistical response. So standards go to standards. So it's the PJ shriek thing.
How about the reducible ones? Do you see any picture?
If they are irreducible, so well, if you compute the tilting and you find the same as in characteristic 0, then I think it's computable, but for each case, not. I don't know.
Okay, let me just thank the last speaker and all the speakers of this morning. Thank you very much.